So what I'd like to do is I'm going to be giving more of a Blackboard style talk using my tablet. It is almost, it's 11:30 p.m. here, so I'm going to count on you all to ask lots of questions in order to keep me awake, because if nobody asks questions, there's some danger I might fall asleep. So please do feel free to interrupt and ask as many questions as you like. Yeah, so I'll be talking about some work that just came out in the last few weeks with Nathan Benjamin and Scott Collier. I'll just start with some very general words of introduction, just to kind of set the stage. So the general goal of what I'll be talking about today is really rather straightforward and somewhat ambitious. And it's not a goal that I'll be able to sort of completely realize today, but I hope to say some things that will hopefully be interesting to you. So my goal is to study quantum gravity in 3 space-time dimensions. And by quantum gravity, I really just mean quantum general relativity with the usual Einstein-Hilbert term, with a constant negative cosmological constant that I've called 2 over L squared here, where L is a length scale that sets the ADS radius. Now, in order for me to define this theory of gravity precisely, I need to not just specify the action of the theory, as I have done here, but I also need to talk about what boundary conditions the theory obeys. So the prototypical solution of general relativity with a negative cosmological constant is anti-de Sitter space. And so the boundary conditions that I'll be interested in is that the space-time asymptotically looks like anti-de Sitter space. So I'll impose some suitable boundary conditions that say that the space-time out at infinity looks like anti-de Sitter space. And it was demonstrated quite some time ago that the set of spacetimes in 3 dimensions, 2 + 1 spacetime dimensions, with asymptotically ADS boundary conditions, has a set of asymptotic symmetries that are given by an infinite dimensional asymptotic symmetry group, which is just the Virasoro group associated to 2-dimensional conformal field theories with a central charge that's given by the ADS radius in Planck units. Okay. And really, one might imagine that this is adjusted by some order 1 number, but at the very least, in the semi-classical limit, the central charge of this Virasoro algebra should just be the ADS radius in Planck units. And although, as usual, I'm setting the speed of light and h bar equal to 1, I think it's worth keeping in mind that if I were to restore my factors of h bar, there would be a 1 over h bar here. So in this theory of gravity, the large central charge limit, I should say the semi-classical limit of this theory of gravity is the same as the large central charge limit of our conformal field theories. And so because of this, it is, of course, natural to organize our study of quantum gravity in 2 + 1 dimensions in the language of conformal field theory. And in particular, we would expect that a 3-dimensional theory of gravity should be dual to some type of 2-dimensional conformal field theory. And in order to try and understand what that 2-dimensional conformal field theory is, what the theory is, the quantum theory that describes 2 + 1 dimensional general relativity, the first thing that we would want to do is talk about its spectrum. So the spectrum of states in this theory. And first, what I'd like to do is just talk classically. So the classical spectrum of the theory. So I'll just draw the spectrum for you on a picture. And what I'd like to do is draw the states in a 2-dimensional picture, where I'm going to label the states by their energy and angular momentum. So in the conformal field theory language, I'm thinking about asymptotic ADS space as a solid cylinder whose boundary is a cylinder, which is a circle times time. And the energy of a state in that picture, if I were to use the CFT language, would be the sum of the left and right moving conformal dimensions of a state, and the angular momentum would be the difference, h minus h bar. So we could then ask, just looking at classical gravity in asymptotic anti-de Sitter space, what sort of states do we have? Well, we have a ground state, a vacuum state, that's empty ADS, which I've indicated here, that has 0 spin and 0 energy. We also have a set of black hole states. So unlike in higher dimensional ADS, there's actually a gap between the energy of the lightest black hole and that of the ground state. And all of the black hole solutions of 2+1 dimensional general relativity live in this triangular region that I've drawn up here. So this is the set of black hole states. The angular lines here, these 45-degree lines, this is just the cosmic censorship line. So for example, if at fixed angular momentum, you were to decrease the energy below this line, then you would have a naked singularity. So the shaded region that I've drawn here is the set of black hole solutions which have a finite horizon area. And I should mention that I've drawn these vertical lines in this shaded region. And those vertical lines should be taken seriously. I'm not just shading in the region here. Those vertical lines indicate that angular momentum is quantized. Okay, so there's supposed to be one of those vertical lines for each integer value of the angular momentum. Now, if you're just considering pure gravity with asymptotically ADS boundary conditions, then it turns out that there are also actually other states in the theory, which are sometimes people call these gravitons. They're probably better thought of as boundary gravitons or edge modes of the theory. So 2+1 dimensional gravity is a theory with no local degrees of freedom, much like a Chern-Simons theory that you would use to describe some quantum Hall system, for example. But even though it has no local degrees of freedom, so there are no propagating local gravitons, no propagating gravity waves, if you study the theory in the presence of a boundary, then there are still edge modes, much like the edge modes in a quantum Hall system. And so these are what we typically call the boundary gravitons of the theory. And if you're familiar with two-dimensional CFTs, then they're really quite easy to understand. They're just the discrete states that you get by acting with one of the Virasoro generators on the vacuum state. So in the language of two-dimensional CFTs, these are the Virasoro descendants of the vacuum. Good. And so in trying to understand how to construct a quantum theory of gravity, so a theory that would be dual to general relativity in 2+1 dimensions, what you would really do is one way that you could proceed is you could try and seek what we might call a theory of pure gravity. So a theory that includes only metric degrees of freedom, which would be a theory some sort of two-dimensional CFT, which is as sparse as possible. In particular, if you were to look at a typical two-dimensional conformal field theory, then it would have a spectrum that looks nothing like the classical spectrum that I've drawn here. In particular, yes, please.
I have a question.
Mm-hmm.
Is it possible that the boundary gravitons, if they be, let's say at a fixed value of angular momentum, if they become very energetic, they can actually go over into the shaded region, black
Yeah.
holes?
So great question. So of course, you can always act with as many Virasoro generators as you like in
Yes.
order to get a very, very high energy state.
Yes.
It could have a state, it could have energy that lives in the shaded region that I've drawn as attributed to black holes.
Yes.
So one question you might ask is whether could you interpret those as black hole states? One simple comment that I'll make is that their entropy is far too small to account for black hole entropy. So for example, a simple counting argument says that the number of Virasoro descendants of the vacuum grows like Cardy's formula with central charge 1, whereas if you're thinking about a semi-classical theory, the number of black hole states grows like Cardy's formula with central charge C, much larger than 1. So really, these boundary gravitons, there's not nearly enough of them to think of them as black hole states. I would rather think of them as, perturbative states, just as if you were studying any old perturbative quantum field theory. And just as you could put a bunch of gravitons in a box, and if you have a lot of gravitons, then they could have as much energy as some black hole, but they wouldn't necessarily, these boundary gravitons we're studying here don't have enough entropy to account for the full entropy of the black hole. Good, excellent question.
Thank you.
Thank you. Great, good. Any other questions? Great. Okay, so the general strategy that we would like to pursue is one where we're trying to seek some sort of theory whose spectrum looks as close to the spectrum as possible. Okay. And so my plan in trying to study this question is I'd first like to begin just by reviewing attempts to construct such pure gravity partition functions. Then what I'll show is that when we try and construct a bit more carefully a conformal field theory that has a spectrum that looks like the one that I've drawn here, that we actually run into some problems. And in particular, we find that there are violations of unitarity. Okay. So in particular, when we do this, we encounter violations of unitarity, which are cured by the addition, well, there are many different ways that this violation of unitarity can be cured. And one way that it can be cured, which I will sort of propose today as a minimal cure for this violation of unitarity, is by the addition of new states in the theory. And in particular, I'll describe the systematic procedure by which we construct a theory that looks not exactly like the one that I've described here, but in a sense as close to it as possible. And this requires the addition of certain sort of a priori mysterious new states in the theory. But I've covered up the title for my talk, but if I hadn't covered it up already, then you'll notice that I've given away the surprise. Because I will then interpret these new states. In particular, I'll interpret them as a certain class of orbifolds. So in particular, I'll say that the strategy that I used up here in order to construct the classical spectrum of the theory was in fact not quite right, because this classical spectrum was derived by assuming that I had smooth geometries. And in particular, I'll propose that we just need to relax this to include a certain natural family of orbifolds. And then this will cure the violations of unitarity that we encountered above. And then I'll present some evidence that this is correct. In particular, I should emphasize that it's only a conjecture that such states need to be added. There are other ways of curing these unitarity violations, but I'll present some evidence, first at the classical level, then at the loop level, and then at the non-perturbative level, before finally ending with a few open questions.
Sorry, Alex,
Yes.
will your analysis be largely of the torus partition function?
Largely, yes. Yes, absolutely.
But you will also talk about whether the spectrum you propose might be consistent with having consistent higher genus partition functions.
Yeah, well, I wasn't planning. I can say things about that. I have thought a little bit about it, but mostly my analysis today will be focused on the torus partition function.
Thank you.
Great. Good.
Alex,
yes.
I'm sure you will talk about it, but I'm just curious, how light is the lightest orbifold state?
It has energy C over 16. So we'll get exactly to that. Yes.
Thank you.
Good. So maybe just to answer that question, a little bit more carefully, the energy of the lightest black hole state, if I use units where everything is dimensionless, has energy C over 12. And what we're going to discover is that one needs to have a certain set of states that accumulate right here that all have energy less than C over 12, but bigger than C over 16. And C over 16 is a magic number for reasons that we will discover.
Okay, thank you.
Or rather for reasons that I may or may not have time to explain, but which I'll try and at least allude to. Good, excellent. Any other questions?
Hello?
Yes.
Sorry. So Alex, I had this question. So there has always been this idea that if pure gravity in ADS3 had a CFT2 dual, somehow it should be something unique about that theory, right? Because the pure gravity is somehow a unique theory. So so there should be something very special and exceptional about that CFT.
Yeah.
So you would be talking about that CFT. So is there? Maybe I'm asking you to reveal your secrets
Yeah. Okay. I mean, if you ask me, okay, let's, it's 11:54 p.m. for me, so I feel free to speak broadly. The original set of ideas that I think underlied a lot of our work in this area was that pure gravity should probably be some highly symmetric, beautiful, truly exceptional object. I think there may be a sense in which that's true, but there also may be a sense in which this is not true. So for example, a lot of work over the last year has indicated that for models of gravity in two space-time dimensions, in fact, these are not individual quantum systems, but are systems that you get by averaging over many individual quantum systems. And I think there's some strong hints that I'll probably get to as we proceed that the same might be true for pure gravity in 2+1 dimensions. So it may be that general relativity is not dual to a quantum system at all, but rather to something closer to like what happens in JT gravity, which is an average over many, many different quantum systems. So in that sense, maybe we should not think of pure gravity as some individual, beautiful, highly symmetric object that exists isolated on its own from all other theories, but instead as something rather more generic.
But if it is indeed dual to some disordered average theory, then how seriously should we try to solve the violations of unitarity?
Well, so very, very seriously. Because, for example, one of the violations of unitarity that I'll get to getting in a few minutes is that it has a negative density of states. Okay, and you can't get a negative density of states by averaging many theories with a positive density of states. The average of many positive numbers is still positive. So the constraints of unitarity are still powerful, even if you're not looking for an individual quantum system. I'll get to that in more detail in a few minutes.
Okay. Yes,
great.
thanks.
But thank you for the question. But maybe are there other questions that don't require me to, reveal all of my surprises? Good. I guess, yeah, great. Okay. So, so let's just begin by asking how we might construct a pure gravity partition function. And in particular, what I would like to do is I would like to imagine constructing the torus partition function of the theory. So in the CFT language, this would be trace of q to the L0, q bar to the L0 bar, where L0 and L0 bar are just the generators of left and right moving conformal transformations. And the way that we would naturally imagine doing this is by performing some sort of path integral. And in particular, because we're now going studying the partition function of the theory on the torus, the finite temperature partition function, that means that we take the Lorentzian theory, we go to Euclidean signature, and you would imagine trying to do a sum over all geometries, that is to say an integral over all metrics with some appropriate boundary conditions, weighted by a Euclidean gravity action. And the boundary condition, of course, is that you're summing over all three manifolds whose metric is a boundary torus with some particular conformal structure that's determined by these parameters tau and tau bar. In a bit more physical language, the imaginary part of tau is the inverse temperature, and the real part of tau is an angular potential that's conjugate to angular momentum. And so the boundary torus then is just given by taking the ADS cylinder and then working in Euclidean time and periodically identifying the two circles with some periodicity that is the imaginary part of tau and some relative twist parameter that is the real part of tau. Good. So, of course, we don't quite know how to compute such path integrals in quantum gravity or even rigorously in quantum field theory. But one plausible way that you could try and attempt to compute such a path integral would be to imagine starting by first finding all of the classical solutions of the theory. That is to say, all of the locally ADS3 manifolds whose boundary is a torus. And then first computing the classical action, okay, which will go like e to the c times some classical action. Remember that c is 1 over h bar, so this is just e to the classical action over h bar. And then computing the series of perturbative corrections around that. And in particular, what one might imagine is that if you could find the infinite set of classical solutions and also compute the infinite series of subleading corrections around each classical solution, then this would give you some sort of exact answer for the partition function of three-dimensional gravity, at least with torus boundary conditions. Now, in order to do this, we first would need to find the infinite set of solutions to the equations of motion, and then compute the infinite series of Feynman diagram corrections. Now, of course, that might sound very hard, if not impossible to do when you first start thinking about it, but actually it turns out to be really not so difficult in the case of 2+1 dimensional gravity. So in particular, the way that this proceeds is by first noting that there are an infinite number of saddles that all will contribute to the sum, but they're all rather easy to understand. So in particular, you're looking for a three manifold whose boundary is a torus. And what are the geometries whose boundaries are toruses? Well, they're solid donuts. Okay? So in particular, you could imagine just taking a torus and filling it in with some solid donut or some handle body. And if you start thinking about it, then you'll actually realize that there's not just one way of taking a torus and filling it in to make a solid donut, but rather an infinite number of ways. And the way that you can characterize the different ways of filling in a torus to get a solid donut is by specifying which cycle is contractible. So in particular, if you were to imagine that we have this picture of anti-de Sitter space that I've drawn here with Euclidean time being the vertical direction, and angle being the phi being the angular direction, then you can fill in this solid torus in any one of a number of ways by taking any linear combination of the angular and time direction and declaring that that is the contractible circle in the bulk. Okay. So here C and D are a pair of integers. In fact, they have to be coprime integers. So the way that we then classify these different saddle points is by just specifying a pair of coprime integers C and D. Okay. And in fact, you can say this a little bit more mathematically by classifying them by elements of SL2Z. And in fact, they're elements of the coset SL2Z mod Z, where you think of an element of SL2Z as a 2x2 matrix with integer entries. And the integers C and D are just the lower rank, the second row of that 2x2 matrix. So that's how you would find the infinite set of saddle points. Now, what we need to do is think about these perturbative corrections around a given saddle point. And
Sorry,
although, yes, please.
Mod Z is because C and D are coprime?
Mod Z is because mod Z is actually, the mod Z is going to be, so mod Z is because you could always, if, for example, you took phi to be the contractible cycle, then you could always, that's exactly the same, how can I say this? Actually, you know what? The mod Z is going to be clear in just a second when I write down my next formula.
Okay. Thank you.
Good. Great. So in order to make this a little clearer, let's just take one particular example. So let's take the example where phi is contractible. So what is that geometry? That geometry is literally just the geometry of Euclidean ADS that I have drawn here, where I take the Euclidean time circle and periodically identify it. So that is the geometry that you would use to compute thermal quantities in an ADS background. So that's the Euclidean geometry that we would call thermal ADS. And then what is the perturbative, so what is the perturbative action of thermal ADS? Well, it's just literally the contribution to the partition function coming from the vacuum state of empty anti-de Sitter space. So that would be a term that looks like Q to the minus C over 24, Q bar to the minus C over 24. So that would be the leading contribution. But then you have all the various descendants. So this is the usual expression for the partition function of a gas of boundary gravitons or a gas of Virasoro descendants in thermal ADS. Okay? So this is otherwise known as the square of the vacuum character of a two-dimensional CFT. Okay? That is to say the square of the vacuum, the character of the vacuum module in a 2D CFT. This brings us back to the question of where did the mod Z come from? Well, in this picture, what is the Z? The Z is the generator that takes tau to tau plus 1. And you can see that this perturbative partition function is invariant under tau to tau plus 1. And where does that come from? Well, invariance under tau to tau plus 1 is literally, so in terms of this picture up here, that is just a 2 pi twist of one of these boundary circles. So instead of identifying with a particular real tau, I'm identifying with real tau plus 1 or plus 2 pi. I'm using units where 2 pi is equal to 1 here. And of course, the fact that this partition function is invariant under tau to tau plus 1 is nothing more or less than the quantization of angular momentum, right? Remember that tau to tau plus 1, that's going to just, so if angular momentum is integrally quantized, then any partition function will automatically be invariant under that. So when I take this SL2Z mod Z, I'm just trying to not overcount by an infinite factor using the quantization of angular momentum. Okay. So then
Alex, I have
please.
a question.
Great, go ahead.
Just a slightly different way of looking at this question would be that we know that the path integral that you talked about above essentially can also be written as a path integral of a product of two Chern-Simons theories corresponding to SL2.
Yeah, I mean,
I
would be a little careful with the SL2 interpretation of this. The rewriting of general relativity in terms of a Chern-Simons theory works very well at the perturbative level, but not at the non-perturbative level. So for example, you can certainly compute this perturbative partition function in terms of an SL2C Chern-Simons theory on a torus. But remember, when we talk about Chern-Simons theory, the usual definition of Chern-Simons theory is as a theory which is a sum over flat connections on manifolds of a fixed topology. But what I'm really doing here is I'm summing over topologies. And so if you want to think about gravity as a Chern-Simons theory, that's not something that you should expect to work at the non-perturbative level. Modular invariance, for example, as we're seeing here, is a consequence of the sum over topologies. And that's not something that's built into Chern-Simons theory. So I think of Chern-Simons theory as some mutilated version of gravity, which works at the perturbative level, but needs to be augmented with something else at the non-perturbative level.
Thank you.
Good. Thank you. Great. Good. Yes.
Yeah, your partition function here is one loop around the saddle point.
Yes.
But presumably you're going to say that the higher loop corrections vanish because of some Virasoro representation theory, because you know that the state is exactly the vacuum.
Absolutely.
That's right?
Absolutely. So yes, so Shiraz has already given the next part of my argument. So you'll notice that these two terms here take the form of a classical action. This takes the form of a one loop correction, and then there's nothing else. The only possible thing that can happen at higher orders is that the value of the central charge gets renormalized. Okay, that's it. So so when I said that we needed to compute the infinite series of subleading corrections around thermal ADS, then I said that I was going to be able to do that, but the way that I'm going to be able to do that is in the stupidest way possible. It's going to be one loop exact. So all of these higher order corrections are going to vanish. And our conclusion will be that the partition function is going to be a sum over all of these saddles of the appropriate perturbative thing evaluated on that saddle. Okay. Good. Great. One comment I'll make is that this one loop exactness of the theory is very much a consequence of the fact that I'm studying the theory with torus boundary conditions. If you work at higher genus, the theory is not one loop exact. Now, nobody's ever been able to explicitly compute the higher loop corrections, but in the same sense that these characters can be thought of as conformal blocks, the perturbative part of the partition function of pure gravity with higher genus boundary conditions is a conformal block, but it's a higher genus conformal block. You can study those things. You can see that they do have a perturbative expansion in powers of 1 over c. You can see that they're not one loop exact. In fact, this is some work in progress that hasn't been published yet. In fact, you can show that that the series expansion of these higher genus conformal blocks in 1 over c is an asymptotic series. You can show that the coefficients have factorial growth, that there are poles in the Borel plane whose locations you can find. Okay. So you can so this one loop exactness is really a special feature of the torus partition function. Yeah.
So, had this been just for the torus case, had this been the block of a state of generic energy, apart from central charge getting renormalized, the energy could have got renormalized.
Yes, we'll
but
discuss
the null state of the vacuum is what protects you, right?
Exactly. So for the vacuum, the only thing that can happen is the central charge. As we're going to get to high energy states that we're going to need to add to the theory, based on the way things are going, I won't have time to really tell you much about the details of the calculation, but you can compute the one loop corrections and you'll discover that that the energies of these get renormalized a little bit. You can actually do that calculation. Yeah. Good.
So Alex, a question. So I was just thinking about this statement that at the higher genus, like you will have higher loop corrections and so on.
Yeah.
But what happens if I have a higher genus, which is almost like, like many toruses connected by some small tubes or something? I would think that, somehow the partition function factorizes.
But it factorizes into torus one-point functions, right? I mean,
okay.
Yeah.
So torus one-point functions or two-point functions if you have two tubes going on.
Yeah.
So those guys also get higher loop corrections?
Absolutely.
Okay, so that's how the higher loop corrections show up in the higher genus. Okay, thank you.
So you should think of this as squares of torus one-point functions with operators propagating between them. So they reduce to torus one-point functions, not to torus partition functions. The leading term, of course, is where the identity operator is propagating here. And in that case, okay, that is one loop exact. But once you start including higher orders in the, so for example, if you were to compute this genus 2 partition function, then there would be some pinching parameter, which we might call Q, an analogy with the torus case. At leading order in the Q expansion, you'll be dominated only by the identity operator propagating here. And then you will find a one loop exactness. Really, it's a product of one loop exactness, but you will find that the perturbation series in 1 over C terminates for the leading order in Q. But once you move into the interior of moduli space, like once you're looking at anything but that leading term, you can show that the perturbation series doesn't truncate. Yeah. And this is something that actually, I'm working on currently with Scott Collier and Nathan Benjamin. And, one can actually study in great detail the nature of this perturbative expansion.
So. Good. Sorry, just one more question. So the statement is that this, let's say if I'm looking at this 2 genus partition function, so genus 2 partition function, then the statement is that one can write down some general expression, which is like some analog of conformal block, but this torus block.
I mean, I would call it a higher genus conformal block. Right?
Higher genus conformal block. And then the statement is that this higher loop corrections in the bulk can be rearranged in a certain way, and the only thing is that the spectrum gets renormalized. Is that? And,
okay. The torus partition function is the thing that encodes the spectrum. The higher genus partition functions encode OPE coefficients as well as the spectrum. Right. So if you want to see that quite explicitly, what you would do is you would think of a genus 2 surface as two sphere 3-point functions glued together, right? So each one of these dotted lines is supposed to be a thin tube. And so this is then a sum of squares of OPE coefficients, where I, J, and K label the operators propagating down those three thin tubes. And so pure gravity is a kind of interesting theory. It's one where the spectrum does not get renormalized in C, but the OPE coefficients do, right? It's an unusual feature, right? So I think that, you know, this is a sort of you know, vague statement, but I think that if you wanted to try and find something that's like a theory of pure gravity, that should be an important hint, right? Which is that the spectrum does not get renormalized, but the OP coefficients do, right?
But isn't gravity somewhat universal? I mean, I would think that OP coefficients also are kind of written in terms of C. Shouldn't everything be just renormalization of the gravitational constant or something?
Yeah.
Am I being naive?
No. I guess what I'm saying is that the spectrum. So indeed, in a theory of pure gravity, to the extent that we can compute it, you can compute these things all as a function of central charge. But what I'm saying is that whereas the spectrum, you know, does not change as a function of central charge, the OPE coefficients do. Right? So, for example, just as a straightforward, you know, in this picture here, the locations of those dots, which are the boundary gravitons, don't change as a function of central charge, right? You know, yeah. L-2, the stress tensor always has dimension 2, no matter what the central charge is. That's an example of such a statement. Good.
Alex,
but the correlation functions of the stress tensor are complicated functions of the central charge. That's probably a good way of saying it. Yeah. Yes.
Sorry.
Question.
Yeah. In all this discussion, are you perhaps assuming that if the pure theory of gravity exists, then it should exist for you know, it's a sequence of CFTs for every central charge, large enough central charge.
Yeah. So
it could be that it exists only for certain central charges and so on.
Absolutely. It might be that it exists for certain central charges. I think what I am trying to do here is understand the constraints. Okay. Ideally, what you would like is a family of theories that exist for many values of the central charge that have a consistent large central charge limit. We're not going to be able to find such a thing. So at this point, I'm only investigating this candidate partition function that I'm calling the pure gravity partition function. And I'm just going to investigate its features. Okay. So in particular, what I'm going to do is I'm going to write this as a, so I'm going to try and extract the spectrum of this theory. So in particular, what I'd like to do is extract the density of states of this theory. So here, I've given you a recipe for computing this partition function, and I'd like to go ahead and extract the density of states here. And what I've written is the density of states as a function of energy at some angular momentum that I've called little j here. And although I've written here the density of states summed over all states in the theory, I could just as well organize everything into primaries and look for the density of states of primaries as a function of energy and spin. Simply by replacing those q to some power to whatever the appropriate characters of the CFT are. So these would be the Verma module characters here. And it turns out one can compute this thing rather explicitly. And what does it look like? So this is then our candidate spectrum for a theory of pure gravity. Well, let me just write down the spectrum of primaries. So it looks very similar to the candidate spectrum that I described to you earlier. In particular, it has lots of states up here in this black hole regime, but it has rather a few problems. Really, it has 3 problems. And this here, just to keep life simple, I'm only writing the spectrum of primaries. So let me tell you what the problems are. So the first is that the spectrum is continuous. When we were talking about the spectrum of the classical theory, that's not a big deal, because in an h bar goes to 0 limit, you always expect a quantum mechanical spectrum to go over to something continuous. ADS gravity, however, is really a theory where you expect a discrete spectrum because anti-de Sitter space is like a box of some finite size of order the ADS radius. So you really would expect a discrete spectrum. And so you might think that the fact that the spectrum is continuous is a problem. The next problem is that there is a negative number of states at an energy equal to C over 12. So in fact, you have a negative delta function appearing right here. And the third is that not only is the density of states continuous and negative with a delta function, but it also has an additional negativity at low twist. What do I mean by that? I mean that if you just look at that function that you get, and you look very, very close to this extremality bound, you actually find that not only is the density of states continuous, but it's continuous and negative. Okay. So this first feature, that the density of states is continuous, that may or may not be a problem. If you think pure gravity is dual to an individual quantum mechanical theory, then it is a problem. If instead you think that pure gravity might be dual to a disordered average of many theories, then it's not a problem. However, these negativities are a problem, even if you think that pure gravity is dual to some sort of disordered average, because averaging over many quantum systems can turn a discrete spectrum into a continuous spectrum, but it can never make the density of states negative. So let's see if we can fix these. And in particular, what I'd like to do is focus on this negativity at low twist. So in particular, this is a very clear violation of unitarity.
Sorry, Alex.
Yes.
A basic question. Is there a way to see quickly that the primaries don't have support over the gap?
That the primaries don't have support over the gap. You mean that there's no primaries in this region? Yeah. I mean, is there a quick way of saying it? I mean, there's this. I mean, the C over 12 is a very important boundary. Yeah, actually, there is a quick and dirty. Well, it depends on your definition of quick. The point is that if you look at, say, this partition function that I've written up here, you'll notice that the ground state has energy minus C over 24, or it has H and H bar minus C over 24. Energy is minus C over 12. That's the statement that the Casimir energy of a CFT on a circle is actually minus the central charge of the CFT over 12. That C over 12 is super important. In particular, what happens is that when we sum over modular transformations, whenever you take a term that is polar, that is to say, comes from energy less than 0, it transforms under a modular transformation to something with energy bigger than 0. Okay. So what's happening is that the modular transformation of the ground state down here is the thing that's turning into all of these other states up here. Okay. And it's roughly speaking this term in the partition function looks like q to the minus c over 24 q bar to the minus c over 24. So these are terms that all diverge as q goes to 0 or as beta goes to infinity. Whereas the terms up here, these are all terms that vanish as q goes to 0. So in terms of the partition function, it's important to think about the terms that remain finite as q goes to 0 and the terms that diverge as q goes to 0. That's really where this gap comes from.
Okay. Thank you.
Sure. Yeah. Yeah. Not sure if that was super useful. Okay. Good. So in order to understand how to cure this negativity, let's just look at it in a little bit more detail. I realize that I've actually already taken up most of my time. I mean, what are the time constraints we're working under here?
We are quite flexible with the time. It just depends on your.
It depends on when I fall asleep. Well, why don't I keep talking and we'll see how things go. And at some point, if I run out of energy, I'll speed up and try and wrap things up a little more quickly. Okay. So let's try and understand that negativity in a little bit more detail. So this primary accounting partition function, let me just write it down for you. And what I'm going to do is, rather than writing rho as a function of energy and angular momentum, I'm going to write rho as a function of what I'm going to call twist and angular momentum. So the twist is going to be like h minus c over 24. So I'm just going to quote what the answer is. I'm not going to go through the calculation at all. So it has one term, which those of you who've studied Cardy's formula will find quite familiar. It basically looks like Cardy's formula. This is the term that we always study when we look at, say, the S transform of the vacuum state in deriving Cardy's formula. But then it has a bunch of other terms. And in fact, because it's 12:30 in the morning for me, I'm only going to write down one of these terms rather than the infinite series of these terms. So it's got these things called Kloosterman sums here, which, if you don't know what they are, don't worry too much. There's some number theoretic objects. And then they multiply something that looks very much like Cardy's formula, but with a different coefficient here. Okay, so these are exponentially subleading to Cardy's formula. Okay. And what we want to do is we want to look at the limit where this twist is very, very, very small. So in particular, typically, this term here is going to be exponentially larger than this term here. So we don't need to worry about these subleading terms. Okay. Then, of course, I should mention there are an infinite number of other subleading terms. But instead, what I want to do is I want to zoom in on the sector here where the twist is very, very, very low, which means h is very close to c over 24. And that means that this twist is going to be something that's exponentially small. And then what happens is that...
Where is the twist? I can't see the T in your first equation.
Oh, there's a T here and a T here.
Ah, thank you.
Yes. Yeah. It's very important. The reason why the twist is exponentially small is that I'm trying to get a polynomial term to compete with an exponential term. So when I say I have to be very, very close to extremality, I'm serious that it has to be very close to extremality. Oh, and by the way, this phenomenon that I'm talking about was actually observed in a paper last summer by Ogori, Shao, Benjamin, and Lin. Yeah. Good. So what happens when the twist is exponentially small is that the second term can be important. And in particular, it can dominate. And so then you need to compute this coefficient here. And it turns out, what is that coefficient? It's some computation that you can do involving these quantities that I've called S here, which are known as Kloosterman sums. And it turns out to be -1. And so what you find is that this density of states is negative. But this problem really contains within it the seeds of its own solution. Why? Well, what we found is that there's a negativity that multiplies an exponential term here. And we know how to get such exponential terms. Because remember that this exponential term came from the S transform of the vacuum state. So if you want to get rid of this -1 here, what you need to do is add a new state whose S transform is going to behave in exactly the same way as this e to the 2 pi times c over 24j. So that's not going to be a vacuum state. Yeah, sorry, but it's going to be a state with positive energy. Yes, go ahead, Sharon.
What we're looking at is large J but small twist.
So in principle, you would think I need to take large J. In fact, you can just go ahead and compute this thing numerically, and it turns out to work even at J equals 2. Okay. So these
Sorry, but when you say exponentially large or small, you mean at large J?
Yes. So for example, if I wanted to make a mathematically rigorous statement that I could prove analytically, I mean that T needs to be exponentially smaller than this quantity here at large J. I should also point out that this spectrum that I'm writing down here is something I can compute numerically, and I can just study it. And you actually find that these negativities exist for all J.
Alex, sorry if I can ask, you just now, you took this limit where T is very small so that the second term sort of dominates, but there's a plus ... and what happens to those terms?
Good, we're gonna get back to that. Great, okay. So it turns out that if T is much less than this e to the -2 pi thing, but much greater than some other term that I haven't written down yet, I can ignore the ... Then in about 30 seconds, I'm gonna not ignore the ... Okay, thank you, good. But what is the upshot? Is that this negativity can be canceled by the addition of a new state with twist that is such that when you plug it into this formula here, it's going to cancel this negativity up here. So in particular, the reason why you got a C over 24 here is because you were looking at the S transform of the vacuum. What you need to do is now include a state with twist 1/4 that, right? So the vacuum state has H equal to minus C over 24. If you want something that gives you a 2 pi instead of a 4 pi, you need a 1/4 that. Or if you were to translate this in terms of H, it has to have an H that's equal to C over 32, if you just plug it all in. Because 3/4 of 1/24 is 1 over 32. Okay, so our conclusion is that if you add in a new scalar state with some energy, that is, so the energy of the state, which is H plus H bar, is C over 16. So that means that it's below the black hole threshold, but well above the vacuum state. And if you do that, you're going to get rid of this negativity. Okay. Okay, but now we get to the dot, dot, dots. Okay. Because it turns out that even if you add one state that gets rid of this particular negativity, there are other terms you need to worry about. And so here I've added one state with dimension c over 16 that cancels this particular negativity. But it turns out that we also need to add more states with other dimensions. So you need to add states with, so here you started out with one with h equals c over 32. Turns out you also need to add a state with h equals c over 27. And then once you add that, it turns out that you're still not quite done. You need to add another state with dimension 5c over 128. And then another state with dimension c over 25, and so on and so forth.
So Alex, this needs to be added at every j or just at j equals 0?
So you only need to add states. So the proposal that I am making here, and this is just a sort of minimal assumption, is that we should add scalars with whatever energy is as large as possible that still cures the negativity. And so what you end up with is a tower of states. So there was one state with h equals c over 32, another c over 27, another 5c over 128, and so on and so forth. Okay. And it turns out, so if I gave you 5 minutes, you could actually discover the pattern here. So the energy, I'll write it in terms of the energy, which is h plus h bar, is c over 12 times 1 minus 1 over n squared. Okay. So although it turns out that in this argument that I've described for you so far with the torus partition function, you only need to add a finite number of these things, for reasons that I don't think I'll have time to talk about too much. The proposal that I would make, which I think is the most natural one, is that you should add such states with all possible integer values of n. There's also one small subtlety that I'm not going to really have much time to comment on, which is that this expression that I've written down is true at large central charge, but there are order 1 corrections that we could discuss. Okay.
Can I ask a question, please?
Yes.
Alex. Are you, in some sense, changing the original theory? I mean, could I imagine that the Einstein theory is sort of augmented by some other matter which gives rise to this cure?
Good. So good. So right now, the strategy that I'm taking is I'm saying, well, I did some pure gravity calculation. It didn't make sense. And I'm coming up with a proposal for what the minimal thing I need to add to this is. And you could interpret this as adding matter to pure gravity. But in fact, I'm going to just interpret it as a modification of what I mean by pure gravity. And I'll do that by giving you a very physical interpretation for what these states are. And I'm going to do that right now, unless there are any other questions.
Thank you.
Good.
Alex?
Yes.
A question. So there was this proposal by, Gabediel and Gopakumar about the coset models, like in this context of having a higher spin theory in the bulk and so on in ADS3. There also you get some spectrum like this. Like
you get tons of states. You get tons more states than this in the theory. If I remember correctly, you actually get an infinite number of states below a finite energy.
Yes, you get a lot of states which are very, very low lying, which are like 1 by 1 and so on.
Yeah. So one of the things that I will emphasize is that these are all states with energies of order the central charge, not order 1. So
Even
these, what's that?
Even if n is of the order of central charge and so on.
Yes. So in particular, in terms of the spectrum, so we have these black hole states. So here. So the lightest state is right here with energy C over 16. Sorry, C over 16. The black hole threshold, I remind you, is C over 12. And then there's another state here with energy C over 27, or I should say energy, so 2 over 27 times C, and so on and so forth. But the point is that there's still a gap here of order C. Okay. So these are not perturbative states.
So this is not a coset-like spectrum. That's what I wanted to ask.
No, I mean, as far as I remember, maybe you or someone else here knows better than I do. As far as I remember, those had lots of states with order 1 energy rather than order n energy. All of the states here have order n energy. I should also emphasize that there's a very quantitative sense in which these are not perturbative states. Okay. In particular, a perturbative state you should be able to form bound states of perturbative states. Okay. And in fact, in a 2D CFT, if you have a state of a given energy, then you could look at crossing symmetry of 4-point functions and use that to infer what people call double twist states, which are basically bound states. And in the context of a 2D CFT, you can look at crossing of 4-point functions in the exact same way. And you can ask, and you can show that generically, if you have 2 states, generically, you're going to be able to form a bound state of them, right? To get other, you know, double twist states and stuff like that. The exception is that this only happens if the energy of the state or the dimension of the state is sufficiently small compared to the central charge. Okay. In particular, it turns out that in a 2D CFT, operators can form double twist states only if they have dimension less than C over 16. So this C over 16 that we wrote down up here is precisely the smallest dimension or the smallest energy a state can have and not form a bound state. Good. Good. So what yes, yeah.
I just want to understand the mathematical statement here. So if I understand right, you're saying that if you take the spectrum that you've told us about, you take the characters and their SL2R, you know, their orbits,
yeah. Mm-hmm.
and you make a partition function which is the sum of these primaries plus their orbits. Then the partition function there will have a completely positive spectrum.
Precisely.
And this is a statement about large enough C. This is true.
Yes. Yeah. So, yeah.
And the claim you have is that if C actually order by order and C, you can correct the spectrum of primaries, the energies, so that it's true in some finite neighborhood, so C larger than 1 million.
Yeah. So maybe I can. Right. Let me. So okay. so I haven't actually made the completely precise mathematical statement yet. There is the precise mathematical statement you can make that, in fact, you can actually get away with adding only a finite number of these states. And you can add a finite number of these states and prove that the partition function that you get by throwing in these characters along with their SL2Z orbits, and summing all that up, gives you a positive density of states for central charge bigger than 3,237.7. Okay, that's just a numerical calculate. That's a numerical calculation. Okay, yeah. But the proposal, I think, the more sort of economical proposal is that you should just add in these states for every integer value of n. Because I think, as we're going to get to in just a second, there's a very nice physical interpretation in that case.
And there also you say that for some large but finite c, for c larger than a large but finite number, you can show that with this new proposal, the spectrum is positive. Is this right?
Yes. There's one subtlety that I'm going to get to at the end if I have time, but basically that's right.
And in order to go through, you need to correct these energies, or this is true for the energies as stated?
I need to add order 1 corrections. Okay.
Thank you.
I'll talk. We can, if you look in the paper, we discuss the order 1 corrections. Yeah.
Thank you.
Good. Thank you. Good. Okay. But let me try and motivate these from a slightly more physical point of view. Okay. So in particular, as other people have noted, these are states that are below the black hole threshold. So you should think of them as particles and not black holes. Okay. And it turns out that in 3-dimensional gravity, a particle will back react on the metric of the geometry, just like it is in higher dimensions. But it will not back react in the way that we're used to in 3+1 dimensional general relativity. But in fact, in 2+1 dimensions, it back reacts in a very simple way. And in particular, it leads to a conical defect of some angle, which is given by this formula that I'm writing down here. So it's 1 minus 1 minus 8GE. Okay. So there's a Newton's constant because that tells you how strong energy back reacts on geometry. And this is the formula for the conical defect angle. Okay. So if you want to picture, the picture that you should think of in your head is that if you put a particle at the origin here, then instead of phi being periodic with period 2 pi, instead you sort of take a bite out of the geometry of angle that delta phi, and instead your geometry is periodic with period 2 pi minus delta phi. Okay. So let's now see what happens to this formula when the energy is c over 12 times 1 minus 1 over n squared. So let's just go ahead and plug that into this formula here, remembering that c is 3L over 2G. Okay, and I'm using units here where L is equal to 1. So this is 1 over 8G times 1 minus 1 over n squared. So that delta phi, just plugging it into that formula, is 2 pi times 1 minus 1 over n. Just taking the square root. And so you can see then that this quantity, 2 pi minus delta phi, which is the periodicity of the angular coordinate, what is that? It's 2 pi over n. So at least as far as the energies are concerned, these look like geometries where ADS3 has been quotiented by Zn. So that leads us to our physical interpretation for these new states as orbifolds. Good. Okay, and what further evidence?
Sorry, Alex,
Yes.
I should have probably asked you this before, but this number of primaries you add at a particular H is just 1. There's no degeneracy or anything. You don't need.
Okay. You know, it's a kind of subtle question. It turns out, so the number of primaries you need to add depends on this coefficient up here.
Mhm.
And it turns out that for the C over 16 state and the 2C over 27 state, and even for the 5C over 128 state, you only need to add one of them. It turns out that you can get away with adding a non-integer number of states for higher values of the energy. Okay. Let's not get into that right now. But yeah, it turns out that you can get away with adding less than one of these states if you wanted to. I don't have a great physical interpretation for that.
But you don't need to. You never need to add 2 states or something or the same H.
Good. It turns out that for the Z2 orbifolds, you need to add 2 of them. I didn't say that. There's a factor of 2. That one has to work out. Yeah.
Okay. But this is known for any H. All the H's, we know the minimum
Yes.
number of
Yeah.
states. That
Yeah, you can look at, there's a table in our paper where you can look it up.
Thanks.
Yeah. Good. Okay. But this is the basic punchline, which is that the energies that are appearing here have a very natural interpretation as Zn quotients of ADS. Okay. So,
Alex,
yes.
The Zn quotient of ADS, do we know the energy of that precisely? I mean, including the order 1 corrections.
We compute, yeah.
And the order 1 corrections, you need match those of the Zn?
Not quite. It's kind of interesting, actually, and I don't have a great interpretation for it. Yeah, so the way, okay, so I can do a 1-loop calculation in general relativity where I can compute the 1-loop general relativity contribution to the energy, and I can try and match it with the order 1 piece that I computed here. And it turns out that they don't quite match. And I don't know exactly how to interpret that. One interpretation might be that there's just some bare counter term for the mass that you need to put in by hand. That's order 1. Or it might be that when I talk about computing, for example, the 1-loop determinant that computes the renormalization of these mass terms, there's some subtle boundary condition at the singularity that you need to think about. And so the naive way that we were doing the calculation didn't quite work. So there's still some puzzles with the 1-loop corrections, with this order 1 correction that I think are still sort of open. But yeah, no, that's a great question. We puzzled about this for a while as to whether we could get those 1-loop terms to match exactly. There's some suggestive structure there, but I don't want to make any real claim.
So, Alex, so just to come back to this question that I was asking before, so these degeneracies cannot be explained by just saying that they are quotients, right? Can you?
Correct.
Okay, so maybe there's some degree of freedom living there, which probably will also correct the, like the energy.
Yeah. So one possibility is that there is some degree of freedom living there. Yeah.
So that might also resolve this Shiraz's question.
It's possible. We spent some time trying to come up with a model for this and didn't you know, couldn't come up with anything. Good question though. Great.
So Alex, in the beginning you talked about earlier you talked about also another source of negativity, this delta function negativity. And
Yes.
that is fixed just by adding a state there. Or it's fixed
So
by
one way that you could, yes, one way, okay, good. So there's another negativity, which was this delta function. So one cure for that actually would just be to add a state here, exactly there. And there's a very natural physical interpretation for that, which is that it's not an orbifold, but rather it is a cusp. Okay. So in particular, that state corresponds to the n goes to infinity limit of the orbifolds that we've been talking about. So in particular, it would correspond not to a conical defect, but to a parabolic singularity rather than, it's what you would call a parabolic rather than an elliptic singularity. So it's a cusp rather than a cone point.
This is the periodically identified Poincare space.
Precisely.
And
exactly, yeah.
Okay, and you get exactly the C-1/12 from that?
Oh, you're asking if I fix, you get C over 12. I don't remember if you get the -1. I'm sure, I bet you do. I don't actually remember. It's been a long time since I did that one loop calculation. Good, actually that's good. I bet you do. I would bet $45. Good. Okay. So this is the basic proposal, that one can add these orbifold states and interpret them as what you need to include in order to address this problem of non-unitarity. There's some evidence for this. One piece of evidence is that, well, I computed their energies and they, at least in the large C limit, agreed with what I needed. There's a bit more that one can do. So for example, in the discussion that we gave here, where we classified all of the solutions, okay, what we're doing is we're classifying all three-dimensional geometries that solve the equations of motion that have a torus boundary. And when I wrote down the set of solutions here, I was classifying smooth geometries. If instead I replace the word smooth manifold by the word orbifold, where orbifold is used in the sense that a mathematician uses the word orbifold, namely something that's not a manifold, but that looks like, you know, Rn mod some discrete group at every point in space-time, then it turns out the only possible orbifolds you can add are precisely the orbifolds that we described below, along with their images under SL2Z. Okay, so you can go through the classification of hyperbolic orbifolds with torus boundary, and you find that these are precisely the geometries that you are allowed to add. There's also some sort of suggestive calculations you can do at one loop. So in particular, what you can do is you could explicitly go ahead and compute the one loop determinant of general relativity in one of these backgrounds. And what you find is that if you compute the one loop determinant using in empty anti-de Sitter space and thermal ADS, you find the Virasoro vacuum character. If you compute the one loop determinant in one of these orbifold backgrounds, you find a Virasoro character, not the vacuum character, but the Verma module character. Okay. So indeed, these orbifold states, according to this calculation, are Virasoro primaries, because computing the one loop determinant in this background gives you a Virasoro character. And finally, there is some sort of evidence that this makes sense at the level of the full non-perturbative partition function. And I don't want to say that I don't want to make too much of this, but I just want to emphasize that there's actually a rather remarkable feature of these orbifolds that occurs when you add them into the partition function. And so let me just comment on that for 1 minute. So in particular, one objection that someone could have made to the proposal that we add these states to the partition function would be the following. So in particular, you could say, well, if you're proposing that we add these states for every integer value of n, then clearly that makes no sense. And the reason it makes no sense is that when n goes to infinity, E goes to C over 12. That means that you're adding in an infinite number of states with a finite number of energy, with a finite amount of energy. Okay. And so that means that clearly the partition function diverges, right? Usually you can never add an infinite number of states with an energy that is bounded above, right? The partition function would diverge. However, so that's true if these were the only states that we were adding. However, it turns out that there's another minus infinity that cancels that plus infinity. In particular, we learned up here that if you just study the image of the vacuum state under modular transformations, you get a -6 number of states appearing right at threshold. So you could say, well, what if I added in my state with dimension C over 16 here? And then you redid the calculation. Well, then it turns out you would get -7 states appearing at threshold instead of -6. And if you added in another state here, you would get -8 states at threshold, and so on and so forth. So in fact, what happens when you add in these orbifold states and do the full sum over SL2Z is that although you have a plus infinity number of states that accumulate at energy C over 12, you also have minus infinity number of states coming from what you might call the SL2Z instantons, or the sum over SL2Z. So although in the the states that we're adding, you appear to be adding an infinite number of them, or if we phrased it in the language of the computation of the torus partition function, there are certain terms in the sum that give you a plus infinity, and then there are other terms in the sum that give you a minus infinity that precisely cancels to give you a finite number. One of the confusing things about this is that we're doing a sum over geometries. Naively, you would think that each geometry is a real geometry, so e to the minus s should be a positive number. So we're getting a sum of a positive numbers. So how could you ever get a minus infinity from that? Well, the answer is that these sums diverge and you have to regulate them using zeta function regularization, as one usually does. But at the end of the day, you get a sum of an infinite number of geometries where the sum over these orbifold states is canceling against a minus infinity that's coming from an infinite number of instantons. And they're conspiring in such a way as to give you a finite answer. Okay. So this may be some indication that this is something to take seriously. Good. So I think that about wraps up the story with these orbifolds, and I very briefly summarized the evidence. I'll make one more comment, I think, which is that, orbifolds appear all over the place in many theories of quantum gravity. So for example, I know that people who try and construct carefully string theories in ADS3 frequently find that there are orbifolds, and very often there are ADS3 mod Zn orbifolds that appear in that case. People who've looked at the localization of supergravity partition functions for ADS2 cross S2 calculations also find that there are very, very nearly identical orbifolds that appear in that case as well. In that case, if I remember correctly, these are orbifolds of ADS2 that appear singular from the ADS2 point of view, but in fact are smooth from a higher dimensional point of view. They're Kaluza-Klein monopoles or something like that. So it may well be that although the solutions that we're looking at here appear singular from the 3D gravity point of view, they're smooth from some other point of view. And the final comment that I'll make is that we've proposed a suggestion which cures the negativity of the density of states, but it very much does not cure, as far as we can tell, the fact that the density of states is continuous. So that still very much is a puzzle. And if you ask me how that's probably resolved, I think it may well be resolved by the conclusion that 3D gravity is dual not to an individual quantum theory, but to a disordered average of many theories. And actually, you know, we have some work in progress on that, which should hopefully appear soon. Good. So maybe I'll just stop here and take any final questions.
Okay, thank you very much, Alex, for a very clear and delightful talk.
Good, thank you.
Let's unmute and thank Alex.
Thank you.
Questions?
Yeah,
Alex,
can I ask a question to Alex? Hi, Alex. This is Gautam.
Hi, Gautam. How are you?
Very good, very good. So, you know, when you had just gravity in asymptotically ADS backgrounds, then of course you had this theorem that all the geometries were simply SL2Z images of asymptotically ADS.
Yes.
And now when you have orbifolding, then also you have the same theorem. It's not completely clear.
Absolutely. So if I replace the word, so there's an argument that has to be, that I didn't go through there. Okay. But you can actually go through the classification of orbifolds of three-dimensional hyperbolic space.
Right.
And show that the only orbifolds that are allowed are first the smooth manifolds, which are not orbifolds at all, or orbifolds by Zn of the type that I described. So you might ask, is it possible to orbifold by Zn cross Zm or something like that? It turns out such a thing is not possible. It proceeds very much just like the smooth manifold classification case.
I see.
Yeah.
Okay, thank you.
You can look in our paper. Thank you. We tried to write it down carefully there. Yeah.
Yeah, and so since you have the orbifold interpretation of these additional states rather than, let's say, scalar fields propagating in the ADS,
Right.
then I guess, so if the interpretation was of scalar fields propagating in ADS, then there are bulk degrees of freedom which now exist, and therefore
I mean, these are very non-perturbative. Their energies are all of order the central charge, whereas a bulk scalar field would have energy of order 1, at least if its mass is of order 1.
Okay.
Unless its mass is of order 1 over h bar, right? You could add a scalar field. It's like if you added a scalar, but that's not a perturbative scalar field, right?
Yes. Okay, good. Yes.
Yeah, so these are all very non-perturbative, right?
Right.
That's an important thing to keep in mind. So you can't build Fock spaces out of them. You can't build bound states. You kind of can't do anything with them.
Yeah, I mean, the context of my question was that, if there are bulk propagating fields, like if there was propagating gravity, you might have imagined that there's some baby universe popping out of some point of the solid torus, and those will be additional geometries and so on. And so that is not allowed because pure gravity would be completely topological. It's the only degrees of freedom are boundary gravitons. But if there are bulk fields propagating,
yeah. I mean, nobody really knows how exactly to define the path integral of pure gravity. The assumption that we made here, which is an assumption, is that the only contributions either come from solutions or from geometries that are continuously connected to solutions. That's what it means. You know, when I said that the path integral should be given by a sum over classical terms plus perturbative corrections, that's exactly what I mean. So what I mean is that I am not including in the path integral families of geometries that are not continuously connected to saddle points. So in simple topological, like in Chern-Simons theories, it's true as far as we understand that the exact partition function is a sum over classical saddle points, in that case flat connections, each of which is dressed by an infinite series of perturbative corrections. But of course, in other more complicated theories, you know, I mean, it may well not be the case. And it may well be that one has to include the infinite set of, you know, you have to include parts of the partition function that are genuine sum integrals over geometries that are not at all connected to, you know, to saddle points. That would be another way of resolving this puzzle.
Right. Okay. Thank you. Thanks, Alex.
Yeah. Thank you.
I have a question, Alex.
Yeah.
I mean, did you or did you not write down the formula for the density of states as a function of energy and J?
I did not write it down because it's complicated.
Oh, I see. I was just wondering.
Yeah.
I mean, you know, this is a natural thing to ask is there some random matrix theory that
that is a great question. I do not know of one. I'm actually, the natural question is whether this partition function is not the partition function of a single CFT, but an average of a partition function of many CFTs. So hopefully, I don't know the answer to that question. I do know that there are other closely related, but not exactly, there are other theories that one can obtain by averaging over spaces of two-dimensional CFTs that look like theories of gravity. So hopefully we'll, you know, we'll be able to write something. Yeah, there should be a paper on that shortly.
So let me just continue the question. Is it that it's the very low-lying states that we expect it to be described in terms of random matrix theory, or it should be for the entire spectrum? Because you have lots of discrete spectrum also, and it's hard to imagine that random matrix theory can reproduce that part.
Yeah. What I suspect, I mean, I take the fact that there's a continuum density of states that we don't seem to be able to get rid of as evidence that if there is a sensible interpretation, it might have to involve random matrix theory. In the sense that, you know, I mean, if you look at the Dyson semicircle law, right, you average n by n matrices, each individual one of which, every Hermitian n by n matrix has a discrete spectrum, of course, but when you average over the space of Hermitian matrices, you get a continuous spectrum. So, you know, I think one of the things that you might very well try and do is I wrote down one term in the density of states here, although I didn't write down the entire thing. You know, this is a square root type density of states, which is the sort of thing that you might be able to get from a, you know, from a random matrix integral. I don't have anything, in the pure gravity case, I don't know how to get this from a random, from an average over CFTs. I mean, one can, you know, there's the JT gravity case where one can do this quite precisely. And I think that's, a great source of inspiration, but I don't have anything quantitative to say right now.
Okay. Thank you.
Thank you.
Alex, you know, the torus partition function does not completely define a CFT.
Absolutely.
So I was wondering whether you might get further constraints when you look at higher genus surfaces.
You certainly will. The problem is that the constraints are rather hard to extract. Yeah, the problem is that they're rather hard to extract. So for example, you know, as you well know, the torus partition function, you know, modular invariance tells you that the lightest state in the theory must have dimension less than C over some number, right? And depending on how hard you work and whether you do it numerically or analytically, that number, it might be, you know, 9 or something like that, 9 point something. If you just try and look at the analogous calculation for genus 2 modular invariance, you also get an energy that is less than C over some number, but it's a weaker bound rather than a stronger bound. So this is one example of a case where, you know, the constraints of modular invariance that I know how to impose actually appear to give weaker constraints at higher genus rather than stronger constraints. Now, that's just the most naive implementation of higher genus modular invariance that I'm looking at. I, of course, expect that if you could really solve the constraints of higher genus modular invariance, you would come up with much stronger constraints. I don't have any very clever ideas for how to do that, though.
Okay, but just continuing along that, these orbifolds are some non-trivial saddle points for the torus partition function that you might not have thought of including when you first saw the problem. Are there analogs of these for higher genus, let's say for genus 2?
Yeah, I mean, there's lots of there's a zoo at higher genus. So there's something kind of interesting that I don't know how well, I mean, you might know this, I don't know how well appreciated this is. But in the torus case, so hyperbolic manifolds, they all take the form of quotients of hyperbolic space. And all of those with torus boundary are handle bodies. What does that mean? That means that you draw a torus and you fill it in. That's what a handle body is. Okay. The quotients of hyperbolic space with genus 2 boundary include both handle bodies and non-handle bodies. So the handle bodies are the things that dominate in pinching limits. They're the things where you just fill in some set of cycles. But there are also more complicated things that can't be interpreted in that way. And these have the interesting property that they only become relevant when you're deep in the interior of moduli space. They're never relevant out near the boundaries of moduli space. Nobody knows quite what to do with these. Yeah, so at higher genus, the story is much, much more complicated. And I think, you know, it's related to the fact that the torus partition function is one loop exact and the higher genus partition function is not. You know, the fact that you can classify all the saddle points with genus 1 boundary and that the perturbative partition function is one loop exact is sort of misleading, because when you study the theory with higher genus boundary, that is to say, when you study things about the theory that are sensitive to OPE coefficients and not just to the spectrum of the theory, it's much more complicated than you would have thought.
Thank you.
Thank you.
Like, one question. So here, essentially thinking about the modular invariance in the torus and unitarity landed you on this model. Does that mean now that so before one was, one wanted to put a gap, bound on the twist, on the gap, the dimension, let's say, of the first excited state, and one was shooting for C over 12. Now, does this mean that one should shoot for C over 16? I mean, bootstrap, modular bootstrap should shoot for this bound to be C over 16?
No,
or,
modular bootstrap is never going to beat C over 12 because you can write down modular invariant partition functions that have gaps of size C over.
With negative things, right, as you said.
Well, no, but sorry, I should take that back. You can write down chiral theories with gaps of size C over 12. So, yeah, there are non-parity invariant theories that have gaps of size C over 12. Yeah, I sincerely doubt you're ever going to be able to beat C over 12. And in fact, there's very strong evidence numerically that you never beat C over 9 point something using modular bootstrap. But it's like, as you know, and as Shiraz was saying, torus modular invariance is just one constraint on the theory. And I think we're just about at the level where we're exhausting what we can get out of torus modular invariance. I think these numerical results of, I think it was Hartman, Tashtini, and Afghani Jedi were very clear and seem to indicate that with modular bootstrap, you're just not going to get better than about C over 9 point something, as far as I understand. Maybe you could do better. No, you should always try and do better. They were just doing the tau to minus 1 over tau symmetry and restricting to imaginary tau axis.
The spinless bootstrap or something.
The spinless bootstrap. The spinful bootstrap might give you a little more.
So the modular bootstrap does not impose integrality, right?
Absolutely not. Correct. It does not impose integrality.
Which is in any case absent in this model, right?
Yeah. There's an interesting paper by Alday and Bay, I think was the other author, where they used a very different approach based on what are known as Rademacher formulas. And the point is that, when we do these sums over SL2Z of something, those perturbative partition functions, these are asymptotic series that diverge. And what they did is a clever rewriting of the constraints of modular invariance, where this is replaced by a convergent series. It's highly non-trivial that this asymptotic series gets replaced by a convergent series. And this is really the technology that I think you would want to use if you wanted to investigate the discreteness of the spectrum. So unfortunately, all of their results, when you try and still seem to give continuous spectra. So I didn't see any way of getting discreteness out of there. But that's definitely the technology that you should look at if you wanted to understand the discreteness of the spectrum. Yeah.
Sorry, I mean, once the spectrum is continuous, there is no meaning to integrality, right?
Absolutely. So I think maybe this is what I think it was Shiraz who said. What you really want to get at, what you really want to do is not just impose the positivity of the spectrum, but the discreteness of the spectrum and the integral and integrality. That's obviously a very, very strong constraint.
All right. Okay.
Okay, I can keep going on and on about this, but it's late enough that I think I might.
Well, maybe you can make your last, what you wanted to say, maybe you can say.
No, that's okay. Well, okay, fine. Okay, I'll say one more thing, which is something that I have found an interesting source of of intuition about this, which is that, you know, modular invariance, if you just look at S invariance, you can actually rephrase everything in terms of Fourier transforms. So if you look at the constraints that the density of states must obey, and rather than working in terms of energy, you work in terms of, if you were working with Liouville theory, you would call the momentum of the Liouville field, the Liouville momentum. Then the statement of modular invariance is literally that the density of states as a function of Liouville momentum is a function that's invariant under its own Fourier transform. Okay. So the search for modular invariant functions includes the search for functions that are invariant under their own Fourier transform. And now, it's easy to find functions that are invariant under a Fourier transform. A Gaussian is invariant under a Fourier transform. But what's hard is to find a function with delta function support that's invariant under its own Fourier transform. Right? If you think about it a little bit, there's one function that you can write down, which is a sum of delta functions that's invariant under its own Fourier transform. The statement that it's invariant under its own Fourier transform is Poisson resummation. Okay. But you could ask, are there other functions that are invariant under their own Fourier transform that have delta function support? And it turns out that the answer is yes. And they have a name in the mathematics literature. They're known as quasicrystals. Okay. Because a function with delta function support, you can think of as a set of atoms, you know, with locations of the delta functions. And the statement that its Fourier transform has delta function support means that if you were to do a scattering experiment, you would find very sharp peaks in that scattering experiment. So one way of having that happen would be to have a crystal, some sort of periodic array. But there are disordered systems, you know, mathematicians know and study disordered systems that also have this property. So I think you can learn a lot. You can get a lot of intuition for this by thinking about quasicrystals. So I'll give you an example. So one example of a function with delta function support, whose Fourier transform has delta function support, is a function with delta functions supported on the zeros of the Riemann zeta function. Okay, the zeros of the Riemann zeta function are distributed in a way that looks completely random as far as if you investigate their statistics. But if you put a function that has support just on the delta functions of the Riemann zeros, and you took its Fourier transform, it also has delta function support. Okay, this is some crazy fact. This is a consequence of the Riemann conjecture. It's some crazy fact.
The Fourier transform is delta function at zeros again?
No, it's Fourier transforms at the logs of the primes. Okay.
Okay, I see.
So, yeah, so this is not a function that is invariant under a Fourier transform, but it's an example of a function that has the sort of property that you're looking for. And I think it's, you know, so I think one lesson that you can draw is that although the function that you can easily think of that is invariant under its own Fourier transform and has delta function support is a nice, beautiful periodic array. But that doesn't mean that there aren't other things out there, you know, things that look basically random, but that have this magical property that they're modular invariant, that, you know, that they have discrete spectrum and things like that. So, you know, I think, you know, this is just maybe a little lesson that, like, you know, there are very complicated objects out there that sort of have this, you know, modular invariance and a discrete spectrum looks like a crazy, incredibly strong constraint. And so it's, I think to me, it seems interesting to think about examples out there in mathematics that have this property. So I think, you know, the zeros of the Riemann zeta is one example of such a function.
Okay, thank you.
Good. Okay, thank you. All right.
I guess,
Thank you.
yeah, if there are no urgent questions, let's, because it's quite late over there. Thank you very much,
Yes.
Alex, for
Okay.
staying up
Thank
so late.
you. Thank you. No, it's my pleasure.
Thanks a
It's
lot.
great to see everyone. Have a great day. Thank you.
Thanks a lot, Alex, for staying up so late and
Yes.
tolerating all our
No, it's my pleasure.
questions.
My pleasure. Okay. Take care. Bye.
Bye.